Thank you, Samson. Good morning, everyone. So today I'm going to be talking not about a study per se, but an actual project that we're going to be designing, and hopefully we'll hit construction here in a couple years. First, I'd like to acknowledge lots of folks have assisted with this analysis. Many of them are in the room here today. From DWR, David Ford Consulting, which was our senior advisor for the project, and many others, the Corps, of course, as well as the reviewers of the work. So the project that I'm going to be discussing today, we call it the Lower Elkhorn Basin Levee Setback. It's a 7-mile setback in the Yolo Bypass, just north of West Sacramento. You can see it in red on the image to the right. Starts just south of I-5 where it crosses the bypass, and then travels about 5 miles south, and also the Sacramento bypass is also set back, and then it ties into the existing levee by the Sacramento Weir. So the intent of the project is to lower the flood risk for approximately 750,000 people living in the lower Sacramento area. It helps add capacity to the bypass for future flood events, and it also kind of paves the way for future projects, both ecosystem improvements in the bypass as well as other expansions in the bypass, including the extension of Sacramento Weir and the potential expansion of the Fremont Weir as well. And this is the first large multi-benefit project that has been planned and actually put into place by the Department of Water Resources that came out of the Central Valley Flood Protection Plan. And it's also consistent with the Corps' American River Common Features, GRR, which includes a portion of the project, the Sacramento Bypass expansion portion, and their GRR also calls out the Sac Weir expansion, which will be a future project. So first, we looked at 4 different alignments that you can see, maybe hard to see, but the one that we ended up picking was the 7-mile setback. Some of the other alternatives included slightly wider expansions into the bypass, like a little notch in the southern portion. However, that one specifically was hydraulically more effective. However, the cost didn't really justify that. As you can imagine, a lot of the negotiation on the alignment had to do with real estate acquisition negotiations with the landowners. Luckily for us, many of the landowners are willing sellers, so that helped us move this project forward. So in order to do the project, we need to get a permit from the Army Corps of Engineers, Section 408 permit. So this permit came out of the River and Harbors Act of 1899. Basically, it gave the Secretary of the Army the authority to permit alterations of Corps projects. However, the applicant, in this case DWR, must prove that the project is not injurious to the public interest and it does not impair the usefulness of the project. So the Corps has an engineering circular which describes kind of the steps to go through to prove that we're not, harming the public interest. And these are the basic analysis steps that we followed. The first one, defining the geographical extent of our study. And then defining what the baseline or existing and authorized condition is. And then developing with project scenarios, both with our project in place, and we also had to look at other future projects that could also affect the system. So as you probably know, the Central Valley Flood Protection Plan called out many different future projects over the next 30 years. This is just one of them, being the first one. And then our next step is to assess the hydrologic and hydraulic performance at each of the index points, and then determine if the results show an adverse impact that we would otherwise have to mitigate. So first step again is define the geographical extent. So a lot of work has already been done in modeling this area. So we kind of had a good idea about the effects of this project. So we looked at basically what is the extent of the hydraulic impacts, both negative and positive. So we kind of took it further probably than we had to, but that was to be conservative. So we went as far north as upstream of the Fremont Weir and as far south as Rio Vista down in the Delta. And we have 18 points that we used for the study. So we were analyzing the system performance at each of these 18 points. So we had to define the existing and authorized condition, also known as the baseline. So this, per the core guidance, isn't only what's in place right now, it's also what's funded and authorized by the Corps. So the completed Natomas levee improvement project, of course, and other projects that aren't necessarily built yet but have been authorized. So we included those all in our analysis. And then we had to define our with project scenarios. So I think initially we were hoping we would just do one with our project in place, but the Corps, of course, wanted to see other projects in addition to our project and see how the system would perform under those future conditions. So this figure here shows many of those other future planned projects that were called out in CVFPP, expansion of the upper Elkhorn Basin, other levee expansions to the south in the Yellow Bypass, tie into the Deepwater Ship Channel, expansion of the weirs, etc. So in the end, we ended up developing 5 with project scenarios in addition to the baseline. So we had our existing with project condition, which just included our project, and we had different configurations of different future projects as well. So what we had to produce in the end is what we call the system performance analysis, the performance at these index points. So we had to develop annual exceedance probabilities. Basically, that is what is the probability of exceeding the design stage at each of these index points. Non-exceedance probabilities or assurance, that's the probability of not exceeding a design stage for a given recurrence interval storm. And then we also had to, by the request of the Corps, look at some deterministic results. So for the 100 and 200 year flood events, what is the change in stage at each of those index points? And one of the complexities is we also, per the Corps guidance, had to look at uncertainty about each of the functions included to develop the annual exceedance probabilities and assurance values. So this is just a schematic of each of the elements of the analysis, starting with the unregulated flow frequency curves, which we got from the Central Valley Hydrology Study. And then running the models, we develop each of these curves as we go. I know that's blurry, so you can't see it, but the end goal is to develop a stage frequency curve. So that's the plot in the lower, at the bottom of the screen. So that's basically what's used to assess or develop the annual exceedance probabilities and other values. So I mentioned Central Valley Hydrology Study. So this is really our basis for developing our boundary conditions that we're going to use for the analysis. However, since that study, there's been one large new project, the Folsom Joint Federal Project. So we used the latest ResSim model for Folsom from the Corps, and we reran that to develop new boundary conditions for the Folsom or American River. And then those boundary conditions were all input into our system-wide hydraulic model. In this case, task order 34 HEC-RAS model, which was initially developed for CV Fed project, has since been updated and expanded. So you can see it goes all the way from Keswick down to the Delta. So yeah, one of the things we had to kind of figure out as we went is how we're going to define uncertainty. So we looked at past studies and kind of coordinating with the Corps, came up with a plan. This is just looking at the hydraulic uncertainty aspect. So we, in our system-wide model, we adjusted Manning's N values throughout the system up and down 20% from our best estimate values. And then we also looked at changing the weir coefficients. So the weir coefficients affect levee overtopping during large flood events. So that significantly affects the conveyance throughout the system-wide model as well. So we have a number of scenarios, 6 in total, and then we have a number of boundary conditions as well. From CVHS, there's 4 historic storm events that were used for that study and 30 scalings up and down of those historic storm events. So that's 120 runs. On top of that, we have the sensitivity runs, which are another 4 times that number. So we have literally several hundred runs for of our model, and then the output is all these data points. So these are plots of unregulated to regulated flow transform and a stage flow transform. This is just an example at one index point. So I just wanted to show this just to kind of make the point that we're dealing with a lot of data here. We used the IPAST tool, Information Processing and Synthesis tool, which was developed during the CVHS days to manage this data. So that tool, which is now a core product that you can all get, is used to fit these best fit regression lines through data sets. And then we also had to do kind of some hand drawing of the uncertainty bounds here. You can see the orange and green lines are the upper and lower uncertainty bounds. So those had to be drawn in to develop, basically develop our uncertainty function. So we use those to calculate standard deviation about these best fit regression lines. So those standard deviation values were all input into FDA, and those were used to calculate our final results. So this is just one example of our annual exceedance probability results. We had 18 points that we analyzed. 16 of those 18 points resulted in no change in annual exceedance probability or a positive change. This is one that had a negative change, so we looked at it more closely. This is just downstream of our project in the bypass. So from the results, you can see annual exceedance probability is going up slightly. We actually call it conditional annual exceedance probability because this isn't really a true AEP. We're not considering levee failure or levee performance. Per the core guidance, we have to assume that the levee is going to hold until the top. So that's one assumption that we're following. So you can see for the existing condition, the AEP is about 1 in 3,300 years, and then for the project in place, that changes to about 1 in 2,500 years. So again, I think our justification is, yeah, we're slightly increasing that AP or risk, but however, that's still way up outside of the bounds of any type of concern. So if the project had been down in like the 100-year range and we were going to like a 90-year level of protection, then I think we would be a lot more concerned. And same thing for assurance. So the Corps also wants us to look at this. So it was kind of hard to understand at first, but for example, the 1% is the probability of not exceeding the design level for a 100-year storm. So you can see from the existing condition, we are at 99.9% probability of not exceeding the design level. For the existing with project condition, we moved to 99.8. So again, slight negative change based on our project, but still insignificant. So the Corps also wanted us to look at deterministic results. So they wanted us to look at 100 and 200 year events and what are the stage changes, since it's a bit hard to analyze those changes in AEP and assurance. So here you can see points throughout the system and the stage changes, all pretty minor for 100 and 200 year events. The biggest stage increase was downstream of our project, the red points and the yellow bypass up to about 1/10 of a foot, which is just about under the Corps threshold for significant adverse impact. Determining whether there is a significant adverse impact is a bit of a negotiation and justification that we have to do with the Corps. We brought them in pretty early on in the project. They were aware of what those would be. So, and we also looked at the future end goal for the bypass system. So including all the projects included in the CVFPP. So under that scenario, you can see all the points are now blue. There's no stage increases once all those projects will be built out. So that's the end goal that they wanted to see as well. So in closing, I think this was a very successful project and analysis. This was the first application of the Central Valley Hydrology Study tools and products for a 408 permit. Previously, the comp study had been used, which was now almost 20 years old. Also, we leveraged a lot of models, CV-FED and CVFPP. That was largely successful. However, system performance analysis can be complex. Of course, we're talking about a complex system of, the HEC-RAS model covers, several hundred miles of channels. So kind of narrowing it down to our project area was helpful, but still, it was still a large geographic area to look at. And then data management is a struggle when we're talking about several hundred runs and dealing with all that data. So definitely QA/QC procedures helped us, as well as IPASS and other data management tools. And again, I'd like to thank our team, many of which are here today. So, and I'll take questions.